Hello, I hope you're doing okay. So 7.4 is a deeper dive into causality. We've talked about correlation coefficient, lines of best fit, R squared, but now we're going to talk about searching for a causal relationship. The most difficult thing we can do in research. So understanding the difficulty of establishing causality from correlation, investigating guidelines that we can use to help establish confidence in causality are the two primary learning goals for today. We're probably never going to say, oh yes, I have 100% proven causality. We can get to the beyond reasonable doubt level, but we are probably going to say we are increasing in confidence in causality. So a correlation may suggest causality, but by itself, a correlation cannot alone ever establish causality. We have to have more evidence and we have to have more information before we can establish that one factor actually causes another. Earlier, we found that correlation between two variables may be a coincidence. There may be some common underlying cause, or there may actually be a causal relationship. Those were the three ideas that we talked about with a correlation. But establishing that number three is basically we've proven that the first two, or demonstrated that the first two have been ruled out. So we can rule out the first two explanations by conducting experiments. If you're in a situation where you cannot conduct an experiment, then it's going to be very difficult ruling out those first two. So we can rule out by coincidence if we repeat the experiment many times using a large number of subjects. The higher number of trials, the more likely you're going to establish this isn't just coincidence. Because coincidences by definition occur randomly, we should not expect to observe them consistently and regularly in several different experiments with different subjects. So while coincidence may confuse the situation in a few trials or a few people, subjects, it's unlikely to be confusing after several trials. We can typically rule out a common underlying cause by controlling and randomizing the experiment to eliminate the effects of confounding variables. We talked about that at the very beginning of the semester as to what a confounding variable is. This way, only the variables of interest vary between the treatment and the control group. If the controls rule out confounding variables, any remaining effects must be caused by the variables being studied. So, if you suspect that one variable is causing some effect, look for situations in which the effect is correlated with the suspected cause, even while other factors vary. Among groups that differ only in presence or absence of the suspected cause, check that the effect is similarly present or absent. In other words, if you think that there is a causal relationship because of the presence of some variable, if the variable is present, you should see the effect. If the variable is absent, you should not see the effect. Look for evidence that larger amounts of the suspected cause produce larger amounts of the effect. That may not always be relevant or applicable, but if you think that something causes, if X causes Y, more of X should cause more of Y. If the effect might produce by other potential causes besides what you think is the cause, make sure that the effect still remains after those other causes are accounted for. If you could remove it, that would be great. You may not always be able to remove it. If possible, test the suspected cause with an experiment. If the experiment cannot be performed with humans for ethical reasons, consider doing the experiment with animals or cell cultures or computer models. And again, if it is something where you cannot test it on animals for ethical reasons, certainly I'm not encouraging you to do that. And then try to determine the physical mechanism by which the suspected cause produces the effect. In other words, if you think that X causes Y, a more difficult question might be, why does X cause Y? Or better yet, how does X cause Y? And if you can explore that, you may get some additional evidence to support your suspicion. There's also such a thing as hidden causality. I think we may have talked about that before. And sometimes a correlation or the absence of a correlation can hide an underlying or hidden causality. For example, studies suggested patients who had heart bypass surgery fared no better than those who didn't. But researchers found that there were some confounding variables, such as the amount of blockage and the surgical technique. In other words, categorizing all heart bypass surgeries into one group may not be fair, because you may have 3 or 4 different surgeries that all constitute heart bypass surgery, and the different technique may have an outcome on the mortality rate of the folks who had the surgery. So those confounding variables prevented the studies from finding any real correlation between surgery and prolonging life. So then what we would want to do is dive in, dig a little deeper, and take those variables into account. So broad levels of confidence, there's really 3. Possible cause. We've discovered a correlation, but we cannot yet determine whether correlation implies causality. So an analogy is the legal system. A possible cause, such as thinking that a particular suspect committed a crime, is often the reason for starting or opening an investigation. Then we have probable cause. We have good reason to suspect that the correlation involves a cause. Perhaps there's because of guidelines for establishing causality. In a legal system, in other words, probable cause is the general standard for getting a warrant to search, or a wiretap, or maybe even making an arrest. So the possible starts the investigation. The probable is where we start taking a person's, I don't want to say rights away, but we start actually infringing upon the person. So we get a warrant to look at their house, we tap them, or maybe even we arrest them. And then the last broad level is cause beyond reasonable doubt. That's reasonable doubt, right? So we're not saying 100% we've proven, but we believe beyond reasonable doubt that there is a causal relationship. So we have found a physical model that is so successful in explaining how X causes Y, it seems unreasonable to doubt the causality. In a legal system, cause beyond reasonable doubt is the usual standard for convictions, and generally demands that the prosecution have shown how and why, and that's that physical mechanism we talked about, the suspect committed the crime. Note that beyond reasonable doubt does not mean beyond all doubt, but we have established enough that we're going to convict this person. We're going to arrest them and put them in prison and so forth. I would like to add just real quickly and briefly that we've talked about this, I think, before. In our legal system, we assume innocence until we prove guilt. So that's why we say that in mathematics, you never prove your assumption. You assume innocence, you prove guilt. And so along those lines, here we would say that if we find a person guilty, or we can find a person not guilty. In other words, you cannot prove innocence because you're assuming innocence. And so in the legal system, they don't say we find the defendant innocent. We just say not guilty, because we haven't established enough evidence to prove the causal relationship. So back to the statistics. Just because you cannot prove a causal relationship exists, in other words, because we cannot prove X causes Y, doesn't mean that we have disproven that X causes Y. It just means that we don't have enough evidence. So the court analogy is one of my favorite analogies in research, because we try to prove the existence of a causal relationship. Usually we can't. But that doesn't mean that we ever prove that there isn't a causal relationship. We just don't have enough evidence to prove that there is one. So just something to think about. All right, this video's gone on long enough. If you have any questions, as always, reach out to me and let me know. Hope you're doing well.